Welcome to lecture 24. In this lecture, we will discuss real-time operating systems based on Linux. So we did talk a lot about different real-time systems in the last class, but we didn't specifically touch on Linux, even though we did mention their existence. So there are different approaches. Again, these approaches are slightly dated, but again, RTAI and Xenomai are still alive as of 2022 in different forms. So we'll discuss the first approach, which is called Montavista, and the second approach, which is a different approach that was adopted by RTLinux, RTAI, and Xenomai. So let's discuss Montavista first. So basically, VRTX used to be, and in many extents still is, a very iconic real-time systems company. So it was later on acquired by Mentor Graphics, which is an EDA electronic design automation company. So this also influenced the development of VxWorks and WindRiver systems, which for a very long duration was the market leader in real-time operating systems. So Montavista Linux was known as hard hat Linux pretty much because in those days, we had different hats, right? So Red Hat Linux was the most popular Linux distribution, and but it had issues with real-time operating systems. So that is why this was known also as hard hat Linux. And gradually this became a full-fledged real-time operating system with support for hard real-time tasks. And the response times were at least as fast as any other RTOS for that era, which is like from 2000 to 2010. So uh, that's when these operating systems were more popular. So they are still there, but then again they have evolved. So Monta Vista basically added a kernel patch. A kernel patch is pretty much a modification to the baseline kernel, where instead of the regular mutex, a priority inheritance mutex was used. So it was a kernel mutex with priority inheritance. And so this was there. And also in some places, it was substituted for non-preemptible kernel level locks. So basically, early versions of Linux and also, some parts of legacy Linux code use one big lock, which is never a good idea for a real-time system. So all of these were converted to priority inheritance mutexes. And also we have discussed the issue with spin locks, right? So we have discussed the issue of spin locks in great detail in the previous lecture and why they are not suitable for real-time operating systems, mainly because of priority inheritance. That is also why they were converted to a priority inheritance mutex and support for high resolution timers was added. So from the website of Monta Vista, as I said, it remained pretty much popular from 2000 onwards. So the preemptible kernel was adopted by the Linux kernel at some point, and then the response time for real-time tasks kept on decreasing from 1 millisecond to roughly 100 microseconds. So it just kept on, getting better and better. And this graph pretty much shows the evolution of the operating system as and when new real-time features were added. So if you look at the Linux kernel, so basically this also evolved in parallel with Monta Vista. So in the first few versions of the kernel, large parts of it, as you can see, were non-preemptible. But gradually, very few small parts of the kernel remained non-preemptible. And as of today, we are at the moment at Linux kernel version 5, 5 plus. So a very small portions of the kernel are actually non-preemptible, which is why even the regular Linux kernel has become way more real-time than what it used to be. And so you can clearly see it from this graph that the non-preemptible red regions have reduced, and that too reduced quite substantially. So what was the need for adding real-time support? Well, the need was mainly audio and video. So if I even if I'm working, I'm compiling code or doing something, if I'm listening to a song, I would expect real-time performance from the audio, otherwise I will see the jitter. So audio was the first thing, then of course video came in, right? And so because of audio, video, multimedia, and now games, there was a need to make Linux far more real-time. And furthermore, symmetric multiprocessors or multiprocessor Linux came in. Its code was by definition preemptible, mainly because we were using spin locks, and also because you have multiple CPUs, we can have more context switching and preemption. So that is why initially there was a dip, of course, in the real-time performance, but gradually more and more features were added, and the real-time performance for multi-core or multi-processor systems improved. So the next approach, other than a kernel patch, so kernel patch is a heavy duty approach. So we will now discuss the other approach, which is RTLinux, RTAI, and Xenomai. So RTLinux was pretty much the first real-time extension for Linux. So had this been a purely real-time, purely open source offering, it would have actually done very well. But what happened quite early on is that the author filed a software patent which covered the real time feature. Because of that, the ecosystem pretty much could not grow, and it did frighten many developers and users. So, this is the way that the urban legend goes. And the fact is that many people who are drawn into Linux are pretty much drawn into because of open source and GNU licenses. So, this is one of the reasons that is cited for RT Linux not becoming that popular. Even the community projects like RTAI and Xenomai went on to become way more popular. In February 2007, RT Linux got sold to Wind River, which, as I have said, is an iconic company. So, Wind River made this the real time core for Wind River Linux. But again, this also ended, the commercial support for this ended in 2011. And so, as of today, which is 11 years after 2011, RT Linux as an entity doesn't exist, even though it has had a significant impact on the thinking of how a real time system is supposed to be designed. So, RTAI, so you can go to this website. So, this was also started at the same time, roughly 1999. But this, on the other hand, was a community project with a large user base, and it did attract a lot of contributors who wanted the open source licenses and who were not all that happy with RT Linux. So this was for x86 because ARM was not back then. And so again, Xenomai is a competitor to RTAI, but of course now there are many more, operating systems in this class. So we will keep on discussing these until lecture 27. So in terms of Xenomai, this was slightly better in terms of the better latencies that it offered, but it is just that it is widely believed that the code is less maintainable and less portable. So Xenomai, on the other hand, was a POSIX RT compliant layer which had a native API, and it could also have skins. So skins are basically these APIs which mimic other traditional RTOSs. So we have looked at PSOs earlier in a previous lecture along with WinRiver VxWorks. So the idea was for Xenomai was to work as a Linux co-kernel, which is basically that it is such a large uh, module on top of the kernel that it pretty much replaces the original kernel, and the preempt RT compilation flag can be used to enable large parts of it in the kernel 3.0 branch, and now of course Xenomai has moved on as a separate project. But the key idea was that the code will never be merged into the mainline kernel. So, what actually characterizes all these three, and we have also seen that earlier, is that the kernel remains, but pretty much these are separate parts, right? So, these are separate parts which may be either loaded as a layer below the kernel or maybe loaded as a large module along with the kernel to take over large parts of the kernel. So that's the idea. So we don't modify the kernel itself, which is what we were doing in approach 1. So building Xenomai, all of these things can be built quite easily. So basically download the source and compile. So the underlying architecture for RTAI and Xenomai is quite similar to RTLinux, right? So for all of them, right? So the key idea is that they don't modify the kernel, but instead they work as a layer which is below the kernel. So for them, the kernel itself runs as the least priority task, lowest priority task, and other real-time tasks compete along with the kernel. So this is the key idea of RTAI, Xenomai, and RTLinux. So of course, they differ in terms of their fine print. So the idea here is that the real-time kernel, which is this layer, right? This is the one that intercepts all the interrupts. Okay. So suppose an interrupt is to cause a real-time task to run, the real-time kernel will do that. But and if an interrupt is for the Linux part of the kernel, then the interrupt will be delivered to the Linux kernel. So pretty much you can think of this as a virtual machine manager or a hypervisor, right? And of course, if an interrupt arrives which a real-time thread needs to handle, the Linux kernel is preempted. So we can think of the hardware, the real-time kernel as a layer around it, and Linux as a layer around that. So in the Linux kernel, we have our hardware, we have our I/O input-output system, we have our hardware interrupts. So they are normally delivered to the Linux kernel, right? So they are delivered to the device drivers within the Linux kernel, and then there are system libraries which primarily communicate with the user processor. So this is a typical setup of a Linux kernel. But in approach 2, what happens is that this basic setup, right? This basic setup changes. So we have our hardware. So we use I/O to communicate with the RTLinux plugin. So this could be a separate layer, or let's say if the baseline Linux kernel supports having such kind of a plugin which can work at such a level, it could be that as well. But pretty much everything happens with the RTLinux plugin. Hardware interrupts are also delivered to the RTLinux plugin. And then we have a real-time scheduler which schedules the real-time tasks, which can also access hardware directly, by the way. So many of them have quite high privileges. And furthermore, Linux and applications on top of Linux are executed as background tasks, in the sense tasks with the least priority. Interrupts can be delivered to them. I/O instructions, messages, even interrupts can be delivered to them, right? So basically, this is done the same way that a regular virtual machine manager would do. Virtual machine monitor, a VMM, also known as a hypervisor, would do, right? So you can think of these as early hypervisors with a certain application area, which in this case is real-time systems. So the features will be the same. We'll have a real-time scheduling algorithm, predictable delays for all kinds of operations, support for fine-grained timers, and a preemptible kernel. So the RT Linux executive is very small. And for the case of RT Linux, you need to bear in mind that the RT Linux executable was in itself or per se not preemptible. But because its routines were very small and fast, this did not cause a big delay. Okay. And then, given the fact that Linux kernel was running as is, kind of unmodified, so that could have different delays and things without guarantees and time bounds and so on. But given the fact that the Linux kernel itself is running as an application now, we really don't care. And of course, there was no support for virtual memory. So that made life significantly easier. So RT Linux and RTA and RTAI, here also, a small real-time kernel would coexist with the regular Linux kernel. EDF and RMS scheduling algorithms were supported. They have to be. So, as we have seen, these are the most optimal in both the classes. So, there is no escaping as such. FIFO was also supported. Furthermore, the real time kernel and the general purpose Linux kernel were decoupled. They could be optimized independently. And the real time kernel was kept small and simple because it really didn't have a big role other than running the real time tasks and running the Linux kernel. And the real time tasks themselves were very nicely structured, right? So it is not that they had a lot of requirements for which you needed a very expressive kernel. For RTAI, the real time tasks communicate with ordinary Linux processes, right, through shared memory channels. So they did allow that. So just think about it. We have a real time task, right? Let's call it an RTT. Then we have the Linux kernel, and then we have an ordinary Linux process. So they could communicate via shared memory. Also, the changes made to the standard Linux kernel were not much because an additional hardware abstraction layer was added, right? And as compared to RT Linux, which is much more invasive in terms of the kernel modifications that were needed, RTAI's changes were quite limited. Furthermore, between RT Linux and RTAI, in RT Linux, as I have said, some kernel source files were changed. And so whenever you change the source files of the kernel, it leads to many problems. So you need to understand that the kernel itself is a very large piece of software. So the moment some change is made, unless there is an absolute consensus of all kernel developers, in subsequent versions, there might be something that breaks the code. So it will increase maintenance overhead. Tracking kernel updates, bug fixing, etc. becomes quite difficult. Hence, this was also one more reason why RT Linux did not survive and why the RTAI branch this survived because it limited the changes to the standard Linux kernel. So one key thing was the hardware abstraction layer. So this is anyway there, right? So in many kernels as of today, this is anyway there. So this is not really a big deal, but in those days, it was a structure of pointers to interrupt vectors and interrupt enable disable functions. So that's there anyway. And also the key point was that the additional layer that we added, right, the real-time kernel, what we are calling, that localized the interrupt handling and the emulation code such that if an interrupt is directed towards a real-time task, a real-time process, it is sent over there. Or if it is directed to the Linux kernel, it is sent there. Right? So the changes were not much and they mostly were customized interrupt handlers, right, which knew where to route what. And the changes were mostly in the hardware abstraction layer of the OS. So the hardware abstraction layer in particular consisted of 5 modules. So there was a module for basic scheduling, right? So this is required because you are dealing with both real-time tasks as well as the kernel, the regular kernel, which is running at the least priority. Multiprocessor schedulers, right? Along with the basic framework, of course. RTAI SHM, which allows memory sharing, which is something that we just discussed, between real-time tasks and regular tasks. And also, FIFOs, so FIFO queues basically, right? That are again needed for information exchange. In terms of interrupt handling, whenever the Linux kernel tries to disable interrupts, the RTAI kernel would intercept that request, record it, and pretty much return a success to Linux. But it would not disable interrupts, right? So, in a certain sense, it will be like a middleman. It will capture the instructions, which it can, right? So, this would be taught in a regular course on virtual machines, how to do that. But the key point is that you pretty much tell the hardware that look, the Linux kernel does not have the functionality, does not have the privilege to actually execute interrupt disable instructions. The moment that is done, a trap is generated, and then the trap actually comes to the real time kernel. The real time kernel then figures out what the Linux kernel has been doing. So it then sets the value of some register, etc., to tell the Linux kernel that its interrupt disabling has been successful. But in reality, interrupts are not disabled, which means when a hardware interrupt occurs, the RTAI kernel first determines where it is directed towards. If it's a real time task, it does whatever is required, including scheduling the task. If it's the Linux kernel, it checks to see what is its status. If the status, let me start bottom up, if it is disabled, it will note the interrupt, queue it, and deliver it later. If enabled, then it will have a pointer to the interrupt handlers of the Linux kernel. So it will directly invoke the interrupt handler, and the interrupt handler would have no way of knowing whether it is being invoked by real genuine hardware or by the real time kernel, right? And in all cases, the interrupt status is recorded. So this is something similar to what a hypervisor or a virtual machine would do, right? So this is like an early virtual machine specifically tailored towards real time tasks. Kernel modules, RTI processes would primarily be kernel modules, effectively a kernel extension. Modules would execute as privileged, have access to the kernel symbol table. So in a sense, they would not be different from the kernel. They would come into the kernel's address space. So there would be no protection per se. A module, given the fact that there is no protection, is pretty much the kernel now. Once it is loaded, it can execute privileged instructions, can execute IO. It can call any kernel function. And also, if there is an issue in the code of the module, it can bring down the entire kernel. That's the flip side. So coming to the real-time scheduler, which is something that is there in the RTAI kernel. So spin locks and interrupt masks, right? So these were our primary methods of scheduling in a regular kernel. They no more have the kind of heft or value in a real-time context. So the basic scheduler is priority based. It has to be priority based. So both fixed and dynamic priority levels are supported, and the context switch time is very low. It's 15 microseconds, right? So this is the most important engineering thing that you need to do here, which is to minimize the context switching time as much and as far as possible. Furthermore, what we have seen, in the case of shared other in Linux, that you can add more scheduling options. So your own scheduling options can be added. And needless to say, the lowest priority is for the Linux kernel, which would again have its own scheduling options inside it. Performance improvement. So system calls normally take a long time to basically change the mode and preempt and so on. But this overhead is eliminated. And the reason it is eliminated is because the real time processes themselves run in kernel space with kernel level privileges, which means that they can directly access IO and access restricted parts of the machine. So you may argue that this will unnecessarily expose the details of the operating system and the hardware to real time processes. Yes, so it basically breaks abstraction. But on the other hand, it gives us the much needed performance. And given that most real time systems are actually, disguised embedded systems, this is not that bad, right? It's complicated, but it's not that bad. So advantage of executing real-time tasks in kernel space, well, the issue of threads being swapped out is not there. Threads have full supervisory permissions, which means complete and full access to the underlying hardware. The RTOS and application pretty much share a single address space, which means that no more do you have to do a system call and a context switch. This is not required. Because it is running in kernel mode, every system call becomes a simple function call within the kernel. And so basically, this is a function call. You can think of it as a software interrupt, but pretty much the idea is that a function call is much, 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 much faster than a system call because it does not involve storing registers, storing the state, right? And then getting into the kernel, doing bookkeeping and all of that is just a matter of a simple, straightforward function call. So the RTLinux scheduler, if you think about it, it treats the Linux kernel as the lowest priority real-time task. We have already seen that. Users can use and create their own schedulers as loadable kernel modules. This makes it possible to either improve what is already existing, in the sense improve the EDF or RMS scheduling, or create your own optimal scheme. Timers, so timers are very important. Timing inaccuracies can deviate a real-time task from its original schedule, right? So this will result in task release as well as completion time jitter, which we have seen. So standard desktop Linux programs, the hardware interrupts have a 1 to 10 millisecond precision. So basically, every 1 to 10 milliseconds, a hardware interrupt is generated. This period of 1 to 10 milliseconds is known as a jiffy, right? So every jiffy, it is true, you do get an interrupt. The interrupt handler also runs, but it need not do much. In the sense, it may just record that the hardware has advanced by one jiffy and then come back. And the typical time quanta, even in Linux, is typically 100 to 200 milliseconds, as we have seen. It's actually 10 to 200, but it's never that low actually. So basically, one process runs for several jiffys, one after the other. RT Linux was one of the first few operating systems to provide a microsecond level of precision. And then, of course, other versions started even going below microseconds to nanoseconds. So, a programmable interval timer, the 8354 chip was used, but now, of course, all of these things have become extremely advanced and sophisticated. So, the real-time timer, which is the timer which is normally under Linux, is set to a 10 millisecond interval, but it's 1 millisecond now. Okay, this information is slightly dated. So, the RTI timer modification, what it did is that the timer will come under a real-time control with its own interrupt handler. And given that the RTOS, the interrupt handler, and the real-time processes all run in the same address space, reading the time is very simple, which is just a function call, right? So this is one more advantage of running all the real-time code in kernel mode. So managing the timer, so we need two kinds of timers in RTAI. One is periodic, the other is single shot. So we have discussed the reasons for both. So the periodic timer has much less of an overhead, the periodic overhead. So normally what happens in a regular timer is that, let's say the period is T, so every time there is an interrupt, you again reset the timer to again alarm, give an alarm at T. So there are a lot of set and reset operations, which is a performance overhead. See, a periodic timer knows that once it is programmed, every T units of time, whatever the unit of time is, milliseconds, microseconds, nanoseconds, whatever, it will generate an interrupt. So this is already programmed into it. So you don't have to set and reset the timer every time an interrupt comes. We also have a one-shot timer. So this is reprogrammed every time the scheduler is called. And there is an overhead, but of course this can be done to measure time intervals to ensure that a process is done before the alarm expires. Also, to look at aperiodic and sporadic jobs, we will need the one-shot timer. Real-time communications, so of course, any kind of a communication would involve the kernel if, let's say, the real-time process is running in the user mode. But given the fact that we are running the real-time processes here in kernel mode, we can use any of these data structures which the kernel normally uses, which are FIFOs, first in, first out buffers, message queues, RPC, shared memory, right? And FIFOs and shared memory in the sense, FIFO queues implemented on top of shared memory. So regardless of these mechanisms, they were, one thing you need to note is that they were quite expensive on a regular Linux system because they involved system calls. In this case, they don't, so that makes them quite efficient. But the king of all mechanisms in terms of performance, not in terms of features, but in terms of performance is shared memory, because in this case, we don't actually have to do anything, no function calls or nothing. Only thing we need to do is that there are some shared pages, and then we need to implement a queue here, and then just keep on reading and writing. So this is, simple. It has the highest performance, but of course, when there are multiple threads involved, we could have a lot of these synchronization induced bugs, and that is exactly why we need talented programmers to write this. But once it is done, the shared memory is the fastest channel. But again, this is for unstructured data like bytes, raw bytes. But if data is structured, message queues in kernel mode and also RPC are not bad options at all. So these are definitely not out of the table. So these are things which for structured data are very good options. So interprocess communication in RTI. So as we have said, the Linux kernel itself runs at a very low priority. So it is something that can be preempted by any real-time task. So communication using standard Linux primitives is not a great idea. So for inter-process communication, simple regular FIFO buffers are used. So this is something quite similar to a first in first out kind of queue, where you have two processes and they establish a queue between them and then they communicate. Biggest advantage of RTAI, well, the source code is available, and another thing is that they allow a large part of the code to be fine tuned, in the sense if a specific part of the kernel or drivers cause an issue, right, a correctness issue, then we can dynamically unload the module. So in a sense, it is a robust operating system. Problems debugging is difficult because we run the application also in the real-time application also in kernel mode. That causes difficulty, right, particularly if there is a bug, and limited set of system calls. So this is mainly because the has to remain small. It cannot be very expressive. Other issues with RTAI, a lot of real-time tasks which are running in the kernel mode cannot make full use of existing Linux system services such as file systems, networking, and so on, mainly because they are not running on top of Linux, but they are running kind of in parallel with Linux. The execution environment is fragile, no doubt. That is because the real time processes run in kernel mode. So, security goes for a toss, protection goes for a toss, isolation, if not done very well, then even containment of a bug or its after effects also goes for a toss. So all of those issues are there, which kind of makes it flimsy. But again, for a real time embedded system, it may not be that bad, case to case. Other issues, so programs are written with a small subset of the POSIX API in mind, and moving existing Linux code to the real time framework can become difficult because it's very well possible that many system calls or many library calls are not supported. So an RTI example would be like this: if this is the underlying hardware with the display, disk, network, and so on. So we can have our graphical system X window, which will X windows actually, which will communicate with the user process. The Linux kernel, which runs as the least priority, lowest priority real-time process. Several applications running on top of it. And then, of course, real-time processes. So the real-time processes would be there, and they would communicate using these RT FIFO data structures with user processes which run on top of the Linux kernel. So this is the broad idea or big broad idea of the system diagram, where you can see what is running in the kernel and what is running in the user space. So these are all in the kernel, these are in the user space, and this is the hardware. So a brief comparison between Linux, RTLinux, and RTAI. So Linux, of course, supports a lot of platforms. RTLinux and RTAI do not, but all of them do support multiprocessors. RTAI, well, at one point of time, it just supported RMS, but the rest, Linux, you know what it supports: shared FIFO and shared RR. So we have seen that earlier. RT Linux used to be the most expressive in the sense it supported both EDF and RMS. Linux supports the full gamut of processes and threads, but RT-Linux only threads and RTI only lightweight processes, which are nothing but threads. They do support a lot of priority levels, as you can see, right? So this is huge, the number of priority levels that they support. Things like memory protection and dynamic memory are not really a priority over here, even though they have, support to different extents. And the same also holds for IPC. That's also not a priority as long as we have one fast mechanism. So same thing, you will have priority inheritance mutexes, so they are required. You definitely need FIFO queues for different processes to talk. So you can see the same thing, semaphores and mutexes, which are priority inheritable, FIFO queues, and one additional thing in RTAI is shared memory, which is again a very fast channel for somewhat unstructured data. So then they support many more things. Priority inversion control, well, both of them, as you can see, they do. Time resolution again depends on the timers that are there. Quality of service, Linux does provide some quality of service, but these guarantees are not explicit. And Linux, of course, supports a bunch of other things, such as the network, file systems, and so on, which, of course, these smaller real-time operating systems do not support. So this finishes our lecture on Linux as a real-time operating system over here. So we will definitely not stop and we will discuss many more real-time operating systems in the subsequent lectures.